Okay, so welcome back. Today we're going to talk about power resistors. Now, if you've ever looked around for high power resistors, you'll see a lot of them like this on Amazon or whatever. And they can be 25 watts, 50 watts, 100 watts, and you can get them in very low ohmic values. So if you want to do like a sense resistor or whatever on your bench, you'll probably be thinking about using these. And there's a couple things you need to know about these if you're going to use them. And one of the limitations they have is kind of surprising. So this one I've got here is 3.9 ohms, 25 watts. I've got one over here that's 100 watts, 1 ohm. And they both suffer, and many of these low ohmic value power resistors suffer from the same problem. Now, the first thing we're going to talk about, there's a couple things I want to discuss here about these power resistors. The first thing I want to talk about is temperature. Now, again, this resistor here is a 100-watt resistor. And in our previous video on thermals, we talked about the temperatures that these resistors can reach at only a fraction of their rated power. So, for example, this 100-watt resistor, 1 ohm, what I'm going to do is I'm going to apply 5 volts. So here I've got 4.9 going up to 5 volts. And there's 5 volts. And I'm applying 20 watts of power to this. So what I'm going to do is I'm going to measure the temperature of this power resistor. See, right now I've got ambient temperature of about 26 degrees centigrade, and with 20 watts I'm going to measure the temperature of this case. Okay, so after a few minutes I'm up to 64, 65 degrees centigrade, and this is with only 20 watts through my 100-watt power resistor, and we're up to 70 degrees centigrade. Now, at these kind of temperatures, you can really burn yourself and hurt yourself. So what you're going to need is to use, and you can see it's still rising, you're going to need to use a fan. I've got a fan here. And also you might want to consider using a big old heat sink like this. It can drop the temperatures quite a bit on your devices, especially these big old power resistors. So word to the wise, make sure you use a fan and a big heat sink if you're going to load these, even at a fraction of their rated power. Make sure you plan to use a fan and a heat sink. Okay, so the next thing we're going to talk about is resistance accuracy. Now, with most of these resistors, you will see specs. Like if you go on Amazon, they really don't have spec sheets, but they will tell you that it's generally plus or minus, say, 5% accuracy resistance. So for example, I've got a 1 ohm resistor here, so it should be plus or minus 0.05 ohms, right? With plus or minus 5% accuracy. So it should be 1.05 ohms down to 0.95 ohms, all right? So it may surprise you that those numbers are fairly useless. So what do I mean by that? Well, I've got a 1 ohm resistor. What I'm going to do is I'm going to apply 5 volts DC across this 1 ohm resistor and measure the current flow on my power supply to see how accurate it is. You know, is it plus or minus 5%? So let's see. I'll turn on my power supply. And here I'll bring it up to 5 volts. So I've got 5 volts. You can see that I'm reading 4.05 amps. And you may notice that this is dropping, okay? If it's 1 ohm, I should be getting 5 amps, but actually I'm getting less, which means the ohm rating, the ohm value of this is more than 1 ohm, okay? And you can see that the amount of current is dropping, which means the resistance is increasing with time. So now instead of 5 amps, I'm getting 3.89. and it's dropping 3.88. And you will notice over time as this thing heats up, and again, this is a 100-watt resistor, and we're only putting in less than 20 watts, and the resistance is increasing, the current through it is decreasing with time. So it's nowhere near plus or minus 5%. You know, we're down to 3.83. That's like 30% off, okay? So it's totally bogus, those numbers. And I've tried that with, you know, a 3.9 ohm, this 25 watt 3.9 ohm resistor. Usually with these resistors down in the 5 ohms or 1 ohm or 0.5 ohms. I've also checked a 0.5 ohm 100 watt resistor, and they all have the same characteristic. Now we're down to 3.80 amps. So again, these things have absolutely terrible resistance characteristics with time. The resistance will go up a lot. It might be 50% increase in resistance over time. So be careful. If you get these, don't expect they're going to be anywhere near their rated resistance when you push any current. If you've got milliamps through them, they're probably within spec. But if you heat them up and put any amount of current through them, the temperature is going to go way, way up. Okay, so to get a little bit better visual picture of what happens to this 1 ohm power resistor as it heats up and the resistance changes over time, what I did is I connected up my lab jack data acquisition unit, and that's connected via USB to my computer, and I've got some software I wrote that will basically just log this data. And the data I'm putting into it is very simple. I'm tapping off the voltage across the resistor and feeding that directly into one of the analog inputs. And then I have a current sensor that takes the current, it's in series here with the resistor, and it takes that current, converts it to a DC voltage proportional to the amount of current. And in this case, it's about 0 amps, gives you about 2.7 volts out here, and then an additional 1/10 of a volt for every amp. So it gives you an indication in volts on how many amps are here. So what I'm going to do is I'm going to take that, I'm going to run this for a few minutes and monitor current voltage, figure out the resistance, and then plot that out to see how the resistance changes over time. Again, it's not really the value that's important, it's the fact that it's changing by 20% or something over a few minutes. Okay, so here we are in Windows, and I've started up my data acquisition software that I wrote that basically allows me to access that data acquisition unit via USB, and you can do things like fast Fourier transform. What we're going to do here is we're going to log the data every second for about 3 minutes or so. So all I need to do is select the 2 channels and hit plot, and it will go and it will save this to a file. So what I've done is I've saved the data to a file, and this is what I get. Basically, I've taken the time and the voltage corresponding to the number of the amps and the actual voltage across the resistor. And what I've done is I've done a little calculation to come out with resistance versus time, and that's what this plot here is. So you can see, and again, I wouldn't rely too much on the actual perfect values of resistance. It's going to be off a little bit. We've got to make sure the data acquisition unit is right and everything. But the relative values over time is what I think is really important. Starting out here, it starts, again, it's a 1 ohm resistor, and it starts out around 1 ohm. And here on the x-axis, you can see I go, here's 60 seconds, 120 seconds, 2 minutes, and here's 3 minutes. So I've run for about 3 minutes. And you can see it gradually changes from about 1 ohm, and it goes up to over 1.2 ohms. So that's about a 20% increase in resistance over a few minutes. And again, that's way, way off compared to the plus or minus 5% that they show you in the ratings. So again, you have to be very careful. Can be very annoying if you're expecting 1 ohm and you get this variation over time. So anyway, I hope that helps. Take care and have a really good day. Thanks.